Good morning, everybody, and welcome to Phasors 4C. Today is actually the last chapter we're going to cover in terms of content, and that is chapter 36. It's all about diffraction. And then at some point, we'll go back into the double slit experiment to see that there is an issue with it that we need to fix in terms of the actual patterns. Today in the afternoon, we're meeting for the lab. This is going to be the last lab, and it's going to be also on diffraction. So that's going to reiterate the stuff that we're going to learn in the morning. On Wednesday, we're going to meet again to do the problems from this chapter, in which case everything for this class is done in terms of content. I mean, we would have covered all the chapters we're supposed to have covered up to chapter 36, which is basically wave optics. So chapter 36 is today, problems Wednesday. Then we will meet, I think we should really meet on Monday, a week from today, which is going to be the 24th, just to make sure we don't miss anything. We have everything covered in terms of content and all the discussions we have, problems also, we discuss them and things like that. Then after that, it's really up to you guys if you want to meet again or not, because by then we would have been done with everything in terms of the content of this course, in terms of problems and everything. So I would suppose at least to the 24th, we're supposed to have regular meetings. Then after that, if an individual wants to meet, I'll be more than happy to meet with you guys. Of course, the 31st, there is no class. That's a holiday, actually. On the 24th, actually, we are only going to meet for the lecture because, as I said before, today's lab is going to be the last lab in terms of labs. So that's where we stand. I mean, there is also a day in June where potentially we can also meet. So it's up to you guys if you want to meet. We can meet in a group or an individual on an individual basis. Again, then after that, of course, have exam 2 online, and then we have the final after that, which is theoretically still going to be held on campus. So did not change anything on that. So that's everything there is in terms of the things that I have in mind, in terms of basically the structure of this class and where we stand on everything. So the final is still scheduled for, what is it, June 7th, I think? June 7th, which is the first day of the second week of June. So that's where everything is right now. The 31st, there is no class no matter what, because of the fact that it's a holiday. And so any questions about where we stand in terms of overall and what we're supposed to be doing, at least for the next several weeks? I mean, toward the end of the semester, I should say. No? Okay, so let's get chapter 36 then out of the way. And once we do that, as I said, we're going to meet this afternoon, which is a very important meeting that we have to have for the lab. It's not really, I made a lot of changes in it so that it just stays focused on the stuff that is related to the last lab. So instead of, I removed a lot of the extra stuff that is from it. So hopefully maybe half an hour, 45 minutes actually for the actual lab instructions. Then after that, you're going to finish it on your own. The lab is due on the 29th, which is the weekend of, not this weekend, next weekend. And that's all there is to it in terms of the things. And of course, I hope to see you guys on Wednesday because it's an important problem session as we're accustomed to. Okay, so let me share with you the screen. Let me bring this closer here. Okay, so chapter 36, we are dealing with the idea that actually light is a wave. Remember, so as a wave. Okay, so basically the point being in here is that we went through the historical context in which light was assumed to be made out of tiny particles, and then we went now with young experiments to the point that no, actually it's more of a wave, and it explains beautifully the double slit experiments. And the double slit experiments, as a reminder again, you have two slits of extremely small size each, and there is a separation between them, d. As a distance separation between them, this is the central point in here, and I have a screen in here where I can see what's going on. So what I see in this case is that the central location, I have a monochromatic light. It's very important to assume that the source in here has the same frequency, same wave, frequency, same omega, if you wish, or f. It's the same thing. I mean, omega is equal to 2 pi f. So it's the same thing. Anyway, so it's the same color. Mono means the same, chromatic means color, okay? So now, in the central location in here, it's going to be a bright fringe. If I move slightly up in here, I'm going to find another bright fringe, and they come in pairs, okay? So if I come in the same distance from the low, I'm going to also find another bright fringe. Between each two bright fringes, there is actually a dark fringe in here. And there is another one in here. And they come in pairs too, okay? The only exception is now is that the bright fringe, there is always a central bright fringe. It's always bright. And now, depending on where you are on the screen, you can find bright and dark fringes. How do you find them, you said? Okay, we worked out the math, and it turns out that d sine theta must be an integer value of lambda, okay? Where m, so in other words, where am I going to go? If I move to a point in here, P, on the screen, well, this point is defined by this angle theta. Okay, so that is the theta that we're talking about. D is the separation between the slits. So this was a double slit. This is chapter 35, by the way, okay, stuff. So now, that means m is an integer in here. M can be 0, which is the central bright fringe, or positive or negative 1, which are the two fringes immediately above and below, or positive and negative 2, and so on and so forth, okay? As long as m is integer. However, there is a limitation into the m actually in here, because of the fact that this equation has a condition at sine theta is m lambda over d. So in absolute value, the sine theta cannot be greater than 1. At most is equal to 1, okay? So as you are increasing the value of m, you have to be mindful of this fact, because lambda is fixed. That is the wavelength of this light. D is the separation that you fix. Unless you make d extremely large in front of the lambda, then if d is small enough, then you have a problem. That m cannot grow willy-nilly, cannot be too big. In other words, there is a limitation on how many bright fringes you're going to see in that. As a matter of fact, that's what you're going to be counting today in the afternoon in the lab, because at some point you're going to have more or less bright fringes. So the value in here, because this is a trig constraint, there is no control over this. The sign is always less than, at most is equal to 1. Therefore, in here, m, which is the number of really the bright fringes above and below, the central fringe is limited. You cannot really have an infinite number of them. Okay. As a matter of fact, we're going to see the constraints today when it comes to the single slit. So what is the single slit now? So that is chapter 36. Assume with me the following. Again, we're doing slits because of the fact that in real life we should really be dealing with a so I have a screen again in here, similar to the first one, because we have to deal with the two-dimensional objects and three-dimensional objects and so on and so forth, okay? So I'm going to draw another one where the source of the beam is. So I'm going to have one, and then copy it and paste it next to it, okay? So what I have in here, I have two, I mean, it's only one basically screen, except there is an opening in it. The width of this opening in here, I'm going to call it A. Oops, A, not D. Okay, just to make a distinction between the single slits and the double slits. So in the double slit, the separation between the slits is D. So this is D is how far apart they are. So the D is the separation or the distance between the slits. Whereas in this case, it's actually the width of the actual slit, because there is only one. Width of the slit, because there is only one of them. There are not two, only one. Okay. So here is the deal. If we make A small enough, okay, what happened? We're going to see also a similar pattern to the double slit experiment. So what happened in here, if I go to the middle, there will be a big, I will call it wide, bright fringe. Again, the light is going to be monochromatic. It's very important to send the same color, okay? At least initially. We'll see how we're going to handle white light. Now, if we move slightly above this one and below it, depending on the size of A, by the way, A needs to be small now, but not too small, okay? In other words, A is still bigger than the wavelength, because if A is smaller than the wavelength, you're going to see nothing in that. It's going to be basically, the entire light is going to be spread everywhere. It's going to be just one big bright light, okay? But A is bigger than lambda, then in this case, you're going to see central bright fringe, and it's wide. So if you look at two different spectra, one of them and you don't know, okay, whether it's double slit or single slit, you can tell. Just compare the sizes of the bright fringe versus the next one, above and below. It's going to be almost twice as much, okay? This is twice as much as the next fringes, and all of the rest of them will be the same size. If they appear, again, there is a condition on the angle, which is coming from Chit. But if they do, they appear in pairs too. So the next ones are going to be also bright. So this is a bright, and this is a bright, and so on and so forth. So there is another bright in here, and there is another bright. Between each two bright, there is a dark fringe actually too. There is a dark fringe in here, and so on and so forth. Okay, so you know how the experiments are going. So this is similar in a sense to the double slit experiment, with the condition in here, with a big distinction actually, that there is a noticeable broad central fringe as compared to the rest of the other fringes. So if somebody gives you two pictures and they have no idea, they did the labs and they were doing double slits, single slits, and now they have the pictures mixed up and they have no idea, and you're supposed to sort them. Just look at the width of the central fringe versus the next fringes, okay? Compare them. You see it is almost twice as much as the others, then you know that you're dealing with a single slit, because they would look the same. And this one will be the same size, all of them, uniform. So you know that it's a double slit in here. So there is a distinction between the two. Furthermore, actually, because in this case, you don't know. I mean, they gave you two films and you have no idea. But the size of the A plays a major role in here. So if you know what's going on, then you know what the source is. So how can we understand this? Obviously, when we did the argument in here, if you guys remember the math, I took a wave in here from this point and another one from here, and I look at the path difference, which I called the delta. And then from there, delta was related to D by this trig identity in here, which is sine of this angle theta, which is the same angle theta, and we did the argument for it based on geometry, that it's equal to delta over D. And from here, we were able to find the condition that this delta must be times K must be multiples of 2 pi and so on and so forth to get it in constructive interference versus destructive interference, and that's how we found bright fringes and dark fringes. So that was the argument for it. We have two clear, distinct sources, whereas in this case, I only have one source. Yet I have interference patterns also where construction and destruction is happening. So here is where Huygens principle comes into play. Remember, Huygens principle says the following. A wave, this is any wave, okay, can be constructed in its journey, basically, while it's moving, okay, from point to point, in its journey by assuming that each point on its wavefront becomes a source of wavelets, tiny waves, if you wish. They're called wavelets, okay? The combination of these wavelets makes the new wavefront. So this is a principle, by the way. This is not an experiment or something. New wavefront, not wavelet. I hope that you guys are already accustomed. We're toward the end of the semester, so I hope that now you're used to the fact that you're supposed to be having a piece of paper and notebook and you're writing these things. You're not relying on me just talking and explaining things, because this is not a movie. You're supposed to be active participants in this process. And at least you're doing these things so that you, first of all, catch mistakes that I make, and you already know that I do. And then also so that things becomes more clearer for you as you go back through the materials and do the problems and things like that. Okay. So this is Huygens Principle. I mean, I put it in my own words. If you look at the book, it has probably different verbiage for it, but let me explain what the principle is. So imagine with me that we have a wave, and somehow it reaches the point in space that this is its wavefront, okay? Can I draw it in the opposite direction? Maybe I can draw better. Yeah, it's the same thing. I'm not good at this vertical drawing in here. So each point on the wavefront becomes a source of wavelets. So this point in here becomes a source of a wavelet that travels from this point in a path that is like this. This point in here becomes a wavelet, a source of a wave that travels like this, and so on and so forth. So this is basically what we're saying in here. They're all traveling with the same uniformity, and I have to really pick them up uniformly spaced. And this is basically where the wavelets are, okay? These are not actual waves. They are actually assumption in here. Obviously, you're going to tell me, how many points do you choose? I tell you, I chose probably 1, 2, 3, 4, 5, 6, 7, 8, or 7, I don't know. How many points are between each 2 points? How many points between this point and that point? Do you know? Any idea how many points exist between 2 points in general? I'm going to take a line. Here is a line. And we're going to take this point on it. We're going to take this point on it. How many points between these 2 points?
Isn't there technically an infinite amount?
So at least there is one. Do you know that? Okay, that's basically what the line is. But you're right, okay? You're absolutely right. So there is another point in here, and there is another point in here, and there is another point in here, and another one in here, and another one in here, and another one in here. So technically, this is not the full picture. There is another wavelet in here of the same intensity, and another one that forms in here. It has the same intensity, of course, and another one that forms in here, and another one that forms in here, and so on and so forth. Obviously, you're absolutely right. So now I'm back to the same question again. How many points between these 2 points? Absolutely right. So there is another one in here. And this picture now, if you imagine with me the process, so actually this is a limit, just like the derivative. When you take the derivative of a function, you do this. and you take the limit of this ratio when delta x you're going to 0. So you're not actually going to take delta x and make it smaller and smaller and smaller and smaller at the end of the day. You're going to assume that if you continue with this process, you define something called the derivative of a function of f with respect to x. So this is just a symbol, not a real thing, not a ratio of two numbers, okay, of this operation, okay, that you actually do, okay? So that's what you do in calculus, and this is similar to it, okay? So what you do in this case, you assume, okay, I'm going to continue making points between each 2 points, which is a process that doesn't end, just like this one, which is a theoretical process. Same thing with this one. Now it's clearly at some point there will be all of these points that will move in here. So this is a little later time, if you wish. So this is at t equal to 0. And this is a little later time at t equal to 0, t equal to t naught, let's call it t. And this is t naught plus delta t, where delta t now can be assumed as small as possible. So the entire wave would have moved from the initial location to the next location. So this is the principle in its explanation, okay? Because it can do a lot for us. It can explain, for example, the interference that we saw before in here. But this becomes just 2-point sources in here, so we don't really worry about them. But for example, in case also of reflection and refraction, we can explain that actually the reflection will happen only constructively when all the waves emerge so that the angle of incidence is equal to the angle of reflection, and the same thing for the law of refraction. So everything can actually be explained in terms of Huygens principle. We need it today here because I want to understand I only have one opening. So if it's only one wave, it should really be just one big wave, okay? It should just be another big light in here. If it is just a point of an infinitesimal small size A. But I'm assuming A is actually not infinitesimal, at least with respect to lambda. It's bigger than lambda. So in this case, this principle comes in handy. So I'm going to look back into that, and I'm going to draw that now, slit, except now much, much bigger than before. So I'm going to make it big, okay? So in other words, I zoomed on it. So it's still the same A in here. So this is the slit in here, okay? But I took a big microscope and I'm looking at it with the big binoculars, okay? Binoculars, so big microscope, okay, I'm sorry. Okay, and now I'm going to assume that the screen, since I zoomed on this, is far away at infinity, is where the screen is located. Obviously, the screen is separated by distance L. Did we use the symbol L or R last time? I think we used R. This is R, and the same angle theta satisfies the condition, oops, from the central location, that it's y divided by r is tangent of theta, the same theta. So tangent of theta is equal to y over r. The same thing like what we did in here. Tangent of theta was y over r, where y is the actual position on the screen of the slits, of the fringes, okay? So the same thing in here, still true. But R now is very big compared to this A. So that's why I cannot draw it, but it's on the other side of the town, okay? It's very far away. So, and I'm going to go to a point P on the screen here, okay? And I'm going to see what's going on in here. So now, assuming that this principle holds true, then what's going on in here, when the wave hits this point in here, each point on it can become a source of a new wave. So in particular, I'm going to take 3 points right now, okay? The top one, the middle one, and the one below, okay? Obviously, you can take one in between them if you like, because every 2 points, there is another point. And then the process, you know what's going on. At some point, I'm going to have an n plus 1 sources. Okay, so I'm going to have an odd number of them, and n separations. In other words, this distance between the actual number at the end of the day is going to be just a over n. Okay, but for right now, I'm going to just take two slits only, basically three sources only. Okay, I'm going to assume that this x is not there, and this central point is not there, just to see it with baby steps. Okay. So it's small, but not that small a. Okay, so in this case, I have only two regions, a over 2, because I have three sources. So I'm going to go to a point far away from it. I'm going to go to a point far away from it. The point is point P, the same point as before, okay? And this one is going to be also far away, and this one is also going to be far away. Obviously, initially they will become parallel, and as the distance increases, they're going to merge. So these lines meet at infinity. So practically they don't meet, they're parallel initially, but they meet at infinity, they meet somewhere of sizes of r. That's where point P is, at point P, which is sitting at infinity, okay? So initially they are parallel, okay? Obviously, this distance is half the whole thing. So this is just a over 2, clearly, and this is a over 2. The difference in path between this one and this one is going to be delta, and it's the same difference in path between this one and this one. It's the same delta. In other words, I took the normal to this, two parallel lines. So this is a right angle triangle. This is the angle theta also, as before. This is the angle theta in here too. Why is it? Because this side of this angle theta, which is the location of the point P on the screen, is perpendicular to this side. That's by construction. Furthermore, this side of the angle theta is perpendicular to the other side of the angle theta, which is just the screen where the slits are located. So these two angles have they have their mutual sides perpendicular to one another, so they must be equal. That is a geometry that we learned a long time ago. It's clear from the geometry in here, the path difference is going to be delta. That is how long one of them took more the other. So in other words, if this is R1, this is R2, and this is R3, R2 minus R1 is what I meant by delta. So delta is going to be R2 minus R1, which is going to be R3 minus R2, which one what I'm calling delta from this geometry in here. The distance, how long one of them traveled versus the other one, okay? So in this case, it's going to be from the geometry, it's clearly, since this is a right angle triangle, and this is also theta, then delta over A over 2 is simply, is sine theta, which means that A over 2 times sine theta is the path difference here between them, where theta is that angle that defines the point P in space. Okay? Obviously, I have so many of these lines, so it's not just this one. I have so many of them, okay? Where n is a huge number that is going to go to infinity if you wish, okay? Very large number, depending, of course, on the size A. It may not go all the way to infinity, but it could be 1,320. Okay? That's a very large number. So for right now, I'm taking two of them, but I'm going to make the following argument. It is easier, or a single slit, easier to find dark fringes than bright fringes. And I will explain why that is, and you will see the math for it, okay? Here is the problem. If this one travels half a wavelength, more or less, it's going to cancel this one. And if this one travels half half a wavelength, more or less, it's going to cancel this one. So as long as this delta is a half wavelength, there will be destructive interference, okay? As long as the difference in path is half of a wavelength lambda, that is, and the difference in path is delta, then we have destructive interference, because one of them comes in like this and the other one comes in like this, and when they meet they will cancel, okay? So as long as the difference in path which is delta is half of a wavelength which is lambda, then we have destructive interference. In other words, we have a dark fringe. Okay, so the first dark fringe can just, this is the first one, because you could have more than one half of a wavelength. You could go basically full wavelength, and the other one comes in a full wavelength also, and they will cancel also still, okay? But opposite in phase, of course. The top half and the lower half, okay? So this is, for example, the top half, this is the lower half. As long as basically half of A and the other one half of A. Now, if you think about this in the same fashion, this is what's going on. If I have 3 points in here, not just, I mean, if I have 5 points in here, I have another one in here and another one in here, then I can still divide my entire fringes into basically half and half. If the top half always comes with a half wavelength ahead or behind the below section, then in this case I will have destructive interference, okay? So this is true no matter how many I take. I took 2 only, but I could take 5, or I could take 7, or I could take 1,337. It's still going to be the same number if the top halves will always be a full half wavelength more or a full half wavelength less than the bottom one. So at the end of the day, I will have destructive interference, and that will be the first one. Because potentially I could have another one where the top half will be a full wavelength, and the bottom one will be full wavelength, I mean, a full wavelength ahead or behind, in such a way that they arrive out of phase, and at the end, I'm going to also have destructive interference. In other words, they will cancel in pairs, okay? The top half, that's basically what we're saying in here. The top half cancels in pairs with the bottom half. To form dark fringes. Okay, destructive interference. So having said that, then here is the first one. The first one obviously is going to be in such a way that A over 2 times sine theta is equal to half wavelength. Okay, cancel the 2 from both sides, and the condition for destructive interference, so this is the dark fringe, the first dark fringe, happens in this way. Okay, we're meeting again with these things in here, man. I'm talking about the STEM center, okay? STEM group in here. Any one of you in the group in here? No. No. Okay, it's fine. We're working on some great projects. I was hoping that more of you sign up for it, but that's fine. Okay, so here's the point. So this is the first dark fringe. The second dark fringe is going to be, again, half of them on top and the other half of them on bottom, but they will be out of phase in such a way you will have 2 of them. So in general, here is the condition, because you will have 2 and so on and so forth, and 3 and so on and so forth. So destructive interference or dark fringes require that A sine theta is equal to m lambda. It looks similar to the bright fringes for the double slit experiment, but it's not the same. So in here, it's dark fringes. You have to remember that, okay? Where m can be a positive or a negative 1, a positive or a negative 2, or a positive or a negative 3, or so on and so forth. No 0, m cannot be equal to 0. As a matter of fact, the central location is going to be bright, because all of them would travel the same distance. So they will be in phase, all of them. So the central location, m equals to 0, is bright. Because there is no path difference between the top half and the lower half. Period. Okay. So m equal to 0 is excluded from this one. And these are the dark fringes. This is when it gets confusing when you're doing exams, okay? And which formula should I use? And they look awfully similar. The other one has a d sine theta in it is equal to m lambda, where m could be 0 or positive and negative 1, positive and negative 2, and so on and so forth. But that was constructive interference for the case of double slit experiment. How would you tell if you're using the right formula? It's because of the d. So look for the d. If it's a distance between two slits, then you use that one. If you're using for a single slit, the only thing you can find are the dark fringes anyway. You cannot find where the bright fringes are. You can, but it's really very, very complicated mathematics. I'm going to give you the formula for it. And if you are in the mood of doing it, go for it, okay? You're going to take a derivative of a very complicated function to find where those bright fringes are. And it's much, much easier to find where the dark fringes are. And then go in the center, and it's going to be a bright fringe. So here is how the deal works now. Use this formula. And this is basically the... So the central fringe is going to be bright. No question about it. You would want to find this point and this point. So this is for m equals to 1, actually. And this is also for m equals to negative 1. So you use this formula. If they gave you A, and if you know what lambda is, so you're going to take A, you take lambda over A, and that's going to be sine of theta 1. Exactly where the angle is in order to find the first dark fringe. Then you're going to use the same formula now for m equals to 2, which is going to be 2 lambda over A equals to sine of theta 2, okay? And it's going to be some value in here. That 2 is actually a dark fringe. So this is m equals to negative 2 and m equals to 2. And this angle that satisfies the relationship tangent of theta 2 equals to y2 over r. This distance from here to here is y2, okay? So you found the dark fringe, the first one. You found the dark fringe, the second one. So somewhere in the middle in here, there is a bright fringe, okay? You didn't calculate it, but you can actually use the same math in here. And this distance from here to here, it's a full wavelength, okay? I mean, a half wavelength, corresponding in this formula in here, and you use it and you find what the distance is. Halfway between them is this way. But now you have, let's say, for example, this is 3.5 centimeters. And this is, let's say, for example, 1.2 centimeters. Obviously, the distance somewhere between 3.5 centimeter, 1.5 centimeters, midway is where your bright fringe is. So finding bright fringes on a single slit is hard. So the easiest way for you to do is use this formula to find the dark fringes, like illustrated in this example. So I found y1, if you wish, using the same formula, tangent of theta 1 equals to y1 over r. Let's say, for example, it's 1.2 centimeters. And r is given to be 80 centimeters or 90 centimeters or 110 centimeters. So r is given. That's the distance between the screen and the single slit. Now you found theta 2, which is somewhere in here. Then between them, smack in the middle, is where the bright fringe is supposed to happen. Okay. So do the math to find where the center of the two is, and you're done. So it's kind of weird in a sense, but that's how it works for a single slit. It's harder actually in a sense. Okay, so let me make the case for the intensity, which is going to be a big deal. Okay, intensity of diffraction for a single slit. Okay, I'm going to give you 3 versions of the arguments for it. The first one is kind of hard a little, but I'm going to give you that just in case if you guys see it somewhere else, you're at least accustomed to it. Okay, I'm going to give you another one, which is used in engineering a lot, and that too requires a little bit of geometry and working things down, but at the end you will see the result. And I'm going to give you the bottom line. I'll tell you, okay, here is the formula and forget about everything else. So that's basically the third version of it. So the first one, here is the point. What we said in here, starting point in here, it has a wave. Obviously, it's traveling with a kr minus omega t, okay? Plus some phase, which we ignore for right now because we're going to assume that this is actually the starting point. Somewhere in the bottom is where the last one is. So this whole distance is a. So what I'm going to do in here, I'm going to take my slit, which is of distance a, and open it, as I suggested in the beginning, into n different positions. So this is all of these divisions are of equal width of distance a over n. So the next wavelet that add up to that one and meets the other one is separated by this distance. Again, this distance is actually a over n. So this is delta now, and each one of them has the same distance delta. So the delta in actuality is going to be given by, this is theta, it's still theta true, okay? Delta is actually a over n times sine of theta. Okay, so far so good. In this formula, so this is the wave, there is a cosine in here of some sort, okay? So the difference in the path between this one and that one is k times that number. So it's k times this one. So there is a phase shift between adjacent, I have to make sure, wavelets of k times delta. And k, remember, is 2 pi over lambda. And delta, I just found this expression in general as a over n times the sine of theta. Okay? So this is basically the general argument leading to it. So I have n sources in this case, n slits, if you wish, n tiny sources. Okay? Now, this is how much phase shift is. I'm going to call this value as beta. Okay? So this is how much angular separation. In other words, the next wave is going to be cosine of kr minus omega t plus this phase shift in the argument. And the next one is going to be plus another beta to this already existing beta, and so on and so forth, all the way until I exhaust all of them until n beta to the last one, because each time I will add a beta until I reach the last one, which is n beta. Okay? So this is basically the argument with the whole thing is, I should have probably used the angle phi because I need the beta for something else, okay? So I'm going to call it phi, I'm sorry. Because the formula in the book actually has a beta in it, so I don't want to confuse the two betas that I'm using. So there's a tiny phase shift phi, and at the end of the day, I'm going to have an n pi. Hopefully you guys are not confused about the symbols. We could have called it alpha, or we could have called it gamma, or whatever we would have wanted to call it. We could have called it angle if we like to call it that way. So the names should not really be an issue in here. But the point being in here is that there is a phase shift between each adjacent, the two adjacent wavelets until I exhaust all of them and I'm at the end of all of them. So here is the deal then. At the point P, it's the sum of all of these wavelets, okay? And each one of them comes with its own intensity E naught, okay? So instead of writing this KR minus omega t, that I'm going to change its name so that the writing becomes a little easier, okay, for my sake. So here is the deal. Then at P, the actual wave is the sum of all of this wave is E naught times cosine of alpha, which is just that KR minus omega t, plus phi, and plus another, I'm going to take E naught because it's common to all of them, cosine of alpha plus phi, which is 2 phi, plus cosine of the same alpha, which is KR minus omega t. I'm just not writing it, the whole thing. That's what alpha is. So alpha is KR minus omega t. That's the actual wave. In each wave or actual wavelet, okay? And each wavelet is shifted from its next neighbor by an angle phi. So it says start from the top one as being the unshifted one. So each one of them will move by phi compared to its predecessor. So it's going to have phi plus 2 phi plus 3 phi and so on and so forth. So it's going to be, the next one is going to be plus 3 phi and so on and so forth until I'm done with the last one, which is a cosine of alpha plus n phi. Okay. So at the end, I added all the wavelets basically. Here is another thing in here that I'm going to use. Euler expression. Are you guys familiar with Euler expression or formula? Which says that cosine of any angle, doesn't matter what that is equal to E I of that angle. I'm sorry. Let me write it differently. E of anything, let's call it X, okay, is equal to cos of X plus I sine of X. Are you guys familiar with this one or not? From your math classes, from your physics classes, from anywhere else?
It's been a while since I've seen it.
Okay. Yeah, so this is Euler expression. If you're not too familiar with it, it's very easy to find the formula for it. Use the Taylor expansion. The cosine is just 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial and so on and so forth. The sine is actually x minus x cubed over 4 factorial over 3 factorial plus x to the power 5 over 5 factorial and so on and so forth. And the exponential in this case is just without the I, okay? But if I have the I in it, it's going to be 1 plus ix over 1 factorial plus ix squared over 2 factorial plus ix cubed over 3 factorial and so on and so forth. You will see that if you add this number and this one multiplied by I, by the way, this is ix. This is going to be negative x squared over 2 factorial because I squared is equal to 1, negative 1, I'm sorry. And I cubed is actually equals to I squared times I, and I squared is negative 1, so this is negative I. So this becomes negative I x cubed over 3 factorial and so on and so forth. So basically you can argue based on the Taylor expansion that this is an identity, and the Taylor expansion works for no matter what the x is. That's why this Taylor expansion is valid and gives me the justification for it. And this is how Euler actually derived this formula. So it's known as the Euler formula. So what I'm saying in here is this cosine and this cosine and this cosine and all of this n cosines, I'm going to take the real part of this expression because the real part is just the cosines. The imaginary part is the non-cosine. So I'm going to ignore the imaginary part. So the sum, because I'm interested in trying to define the sum. So here is the wave then, okay, is going to be the real part of this sum of the exponential of I alpha plus nothing. The first one is actually alpha. Did I forgot to include the initial one. The initial one had no alpha in it. So we have to really include the first one first. Cosine of alpha plus the next one plus the next one plus the next one. So it's actually cosine of alpha only plus I alpha plus phi plus I alpha plus 2 phi plus and so on and so forth until we reach the point where it's exponential of I alpha plus n phi. Okay. Obviously, I need to find this sum. Once I find what this sum is, I'm going to take its real part. So that's where the thing is. So I'm going to call this sum S of n. Once I find it, I'm going to take its real part and we're done. So we have a complex number in here, S of n, which is equal to exponential of I alpha times. Because I have the exponential of I alpha, which is common to all of them. So I'm going to take it out. So I'm going to be left with 1 plus exponential of I phi plus exponential of 2 I phi plus exponential of 3 I phi plus until I have exponential of n or I times n phi. Okay. This is actually a geometric sum in here because exponential of 2 I phi is exponential of I phi squared. Exponential of 3 I phi is exponential of I phi to the power 3 and so forth. So this is a normal 1 plus u squared plus u cubed and so on and so forth, all the way to u to the power n, because u, I took it to exponential of I phi. That's all. Okay. And this is a geometrical sum that we know how to find, basically. All I have to do is just add one extra term and subtract it immediately, and we're in business. So plus u to the power n plus u to the power n plus 1 minus u to the power n plus 1. And this, I'm going to move it to the first term. So this is going to be 1 minus u to the power n plus 1 times plus, I'm sorry, times nothing, plus u times, I would be left with 1 plus u squared all the way to the last term in the sum in here, in this sum, is going, since I moved u, is going to be u to the power n again, which is the actual sum that I want in here. So if this sum now is a smaller sum, s of n, because I took that exponential out. So this is going to be s of n again, which is the actual sum. And hopefully you guys are not too, that you did already geometrical series like this one in here. So this is s of n is equal to 1 minus u to the power n plus 1 plus u times s of n. Move s of n to the other side and basically divide by its coefficient. So it's going to be 1 minus u in here, and it's 1 minus u to the power n plus 1. And the only thing in here is I need to restore my u, which is exponential of I phi, and I have an exponential of I alpha in front of it. And the exponential of I alpha is not going to matter in this case because it's going just a factor multiplying everybody. So let's find it now, everything in here. So I have this sum in here that I'm going to write it as s of n now is exponential of I phi, alpha times this whole thing, which is 1 minus exponential of I n plus 1 times phi over 1 minus exponential of I phi. So this is basically the same sum. So this is this complicated sum in here, okay? If you're not familiar with complex numbers and exponentials, this may sound too hard for you, okay? So if it does, please review it again and see if it makes sense to you. If you have difficulty with it, I'll be more than happy to discuss it in more detail on how to go from term to term. When we have a complex number, this one, and we're headed toward find this real part because we really need to find this real part here, because it doesn't make sense to work with complex numbers when we're dealing with intensity. So we need to find its real part. So we have to multiply by the complex conjugate of the denominator, which is in this case exponential of minus I phi, and numerator and denominator, and then do the algebra. The denominator will be just the absolute value of this thing in here, and the absolute value of 1 minus exponential I phi squared is going to be, remember, it's 1 minus cosine of phi plus I sine of phi in absolute value squared. I mean, what I mean by the modulus of this complex number, which is the real part squared plus the imaginary part squared. I mean, without the I, of course. So this is going to be 1 minus cosine phi squared plus sine squared of phi. This one involves 1 plus cos squared phi minus 2 cos phi, and this one plus sine squared phi. This one plus that one is 1 plus 1, that's 2. So we'll be left with 2 minus cosine of phi. And 2 minus cosine of phi is almost there. We have 2 times 1 minus 2 sine squared of phi over 2. The 1 and the 1 cancel, and this whole expression, negative and negative, becomes pi cancelled. So the denominator is 4 times sine squared of phi over 2. So the numerator, we're done with it, and it's a real number, and we need it to be a real number because we need to get rid of the denominator in order to. Now we have to deal with the numerator and find this real part. Okay. Let me give you the bottom line. Okay. First of all, you're going to multiply the numerator. So let's find it at least in a closed format and then do the. So S of n is exponential of I phi alpha times. The denominator now is all real, 4 sine squared of phi over 2, okay? The numerator will involve stuff in here. The numerator, which is really the complex part of this whole thing. You have 1 times 1, which is 1, which is real, okay? Times the cosine of alpha in this case. And you have 1 minus this exponential, okay? And then you have a negative, this exponential times 1. So you have a negative exponential of I times n plus 1 phi. And finally, you have an exponential of I n plus 1 phi times an exponential negative I phi. The negative and the positive 1 will cancel. So it'll be just left with an exponential of I n phi. Okay. Work out the algebra in here, okay? There is a real part in here, and there is an imaginary part in here. The real part in here for this one is identical to the first one. As a matter of fact, this is 1 minus cosine of phi. And the imaginary part has a minus in it because of this one, sine of phi, okay? This one also has a real part and an imaginary part, and the real part is just minus cosine of n plus 1 times phi. And the imaginary part has a minus again in it of I sine of n plus 1 phi. And this one has a real part in it, which is cosine plus cosine of n phi, and an imaginary part, which is I sine of n phi. Here is the problem. The real part of this expression combines with the real part in here, which is here, and here, and this one. The imaginary part in here, which is an I sine of alpha, will combine with the imaginary part in here, and the imaginary part in here, and the imaginary part in here, and that is the real part. You do this one, and you do trig identities, and you're going to find the answer, okay? You're going to find the sum in here, and when you do that, you're going to have an expression for the amplitude of the wave. Once you have the amplitude of the wave, you are in business. You have found the actual wave. There is this method, okay? So I didn't finish the calculation in here because it's kind of long. So probably what I should do is I'm going to finish the calculation separately. I'm going to post it on Canvas. If you have difficulty understanding, basically, from this point on, is just finding the real part. That's all, okay? Once you find the real part, it's not over yet. You really have to do some trig manipulations to find the final answer. So there is another method. So this is one, complex numbers. So this uses complex numbers. If you think you get lost in it, so this is the complex numbers method. And it's a good idea to know how to work with complex numbers, because as engineers, you really find it a lot easier to do complicated circuits with complex numbers. As a matter of fact, the saying is, when you have a difficult problem, try to use complex numbers. They will make it easier. Okay, sounds kind of an oxymoron, but that's exactly what it is. Now, when it comes to the second method, which is the Phasors method, have you guys done the Phasors method somewhere in your physics classes or somewhere else in your engineering classes? Familiar with it or not? If you don't know, that's fine too. Because I'm going to give you a brief intro to it. Yes, no, maybe. Or have you ever heard of it? Come on, guys. I promise this is the last proof that you're going to have from me in this class, okay? So I know we've been doing a lot of math stuff. That's times I probably forgot we're doing physics. No? Okay, let me show you what the Phasors method is. Here is the deal. We're dealing with waves, of course. I'm going to take a wave of phase. I'm going to take it in 1D, okay, to make just an omega t in it, okay? Of phase omega t, okay? So here is how it looks on the trig circle of radius 1. This is the amplitude of the wave. This is its projection on the x-axis. So if it's moving on this axis with an angular velocity omega, so it has an angle omega t at some point in the future, okay? It started from 0. So this is basically a times cosine of omega t. So the amplitude is big A. So this is a cosine of omega t. It's this wave, okay? So at t equal to 0, this is a, and then it moves around and comes in circles. So this is its phase. So if I have to add to it another wave, let's say, for example, let's keep the same amplitude in here to make life a little easier, of a different wave with a different phase, okay, shifted by phi. So it's the same wave as before, except now it's shifted by an angle phi. So it's the same angle before omega t plus phi. So this is how it looks like now, the new one. So this is the new phase. So the Phasors method says, find the sum of these two vectors, basically. So this is a cosine omega t plus a cosine of omega t plus phi. And the amplitude from this geometry is going to be the amplitude of this new wave, okay? And the phase is going to be given by this angle, which is less than omega t plus phi, but more than omega t. So it's an angle between them. And if you do the geometry, you're going to find it. As a matter of fact, this is not hard to do with trig functions too. So it's going to be a cosine of omega t plus a cosine of omega t plus phi. And if you use the sum of the angles formula, so this is going to be cosine of omega t plus phi divided by 2. So it's going to be omega t plus phi over 2 times cosine of the difference between them, which is omega t minus phi over 2, okay? So if I use the formula for the sum of the triangles, sum of the cosines, we're in business. So actually this is the new wave. It's going to have a cosine of, I'm sorry, there is a 2 in the formula. So it's going to be a 2a, omega t plus omega t, that's omega plus, divided by 2, that's omega t, plus phi over 2, cosine, in this case, of the difference between them, which is just phi over 2, okay? I mean, it's a negative phi over 2, but the cosine is an even function, so that's why I dropped the negative sign in there. So that's basically the new amplitude then is clearly equal to 2a cosine of phi over 2. And the phase now, with respect to the initial one, is omega t plus phi over 2. In other words, this distance in here, from here to here, if you use a ruler, is going to be 2a times cosine of phi over 2. If it is, and the actual angle in here is going to be omega t plus half this angle. So that is basically what this formula is saying in here. So in other words, if phi is equal to, let's say, for example, pi, in other words, this is the first one went this way, and the second one is this way. So in other words, the phase difference is equal to pi. If it is equal to pi, then in this case, how much the sum of the two vectors is going to be 0, because both of them have the same length. So this is going to be 0 because we go from point and come back to the same point. So in this case, the cosine of phi over 2 is a cosine of pi over 2, and that is 0. So this is true. if the phase difference phi is actually equal to 2 pi, then in this case, cosine of, so in other words, one of them goes like this, and the other one, so let's take it phi equal to 0 first. We did phi equal to 0, so we need to do phi equals to 2 pi. So this one is a 2 pi initial of the other one, so it's going to be a cosine of 2 pi over 2, which is a negative a. Okay, so this one will travel. So how am I going to draw it in here? With a phase difference that is equal to 2 pi. It's hard to conceive in here, but the point being in here, it's going to be, because we're going to take the square of the amplitude in here, because at the end, the energy, the intensity depends always on the square. So it's going to be the same sum. So it's going to be 2a times squared, which is 4a squared. Okay. So in other words, this will give me how I'm going to add the angles in here. Okay. Oh, yeah. I'm sorry. So it's going to be negative. You're right. So you're saying in here, this is going to be cosine of 2 pi over 2, which is going to be a negative 1. That's true. But don't forget, you have also a pi over 2 in here, because 2 pi over 2 is going to be a pi, and cos of omega t plus pi is actually going to be a negative, which cancels that negative and is going to be positive. So in other words, if you go full 2 circle, and this is a and this is a, the sum is going to still be 2a, because there is a negative phase in here, a negative 1 in here, but there is another negative 1 coming from the cos of any angle plus pi. Okay, in other words, the cosine of this angle omega t is here, and the other one is omega t plus phi, which is this angle actually, and its cosine is actually here. So the two cosines are actually equal in magnitude but opposite in size. So there is a negative pi, a negative 1 in here, and there is a negative 1 in here, which makes it positive, which is good, all in good. The point being in here is you can do any construction you want to, instead of doing it with trig functions or the exponential in here, which is kind of hard. You can just use this Phasors method and it's going to work the same. Okay. Having said that, let's go into my problem, my original problem in here. So in the central fringe, so what I have in here, I have the top source sending its wave, and it's in phase with the second one from the bottom. So the next one is in here. This one is in here. And all of them, they are actually in phase with one another. So if I have n divisions in here, and at the end they will add up, so that they will give me, each and every one of them will come with its own intensity E naught. So I have n E naught, and when I add them up, let's say for example I have 1, 2, 3, 4, 5, 6 of them in here. So I have 6 times E naught, they will add up to give me the central fringe, which is bright. Okay. Now if I move a point P in here at an angle, this starts to bend, because the first one will be slightly shifted from the next one. So this is my starting point. This is the point now on the print. So the first one is slightly shifted. The second one is slightly shifted, and I keep on making them slightly more and more. I should have 6 at the end of the day. 1, 2, 3, 4. I made it too big in here. Let's make the point closer in here. So this is a point P. Okay. So in this case, initially it was in here, but now it's shifted. It started to tilt a little. Okay. So at some point, if I move far away on the screen, the phase shift starts to become a little bit more dramatic in here, until I get to the next point. If I keep on doing this, at some point, this will look like this. So my starting point will shift. Let's make it a bigger shift. And the second one will shift more, and the third one will shift more, and the fourth one will shift more, and the fifth one probably will shift more, until I come back to the starting point. So in this case, I have destructive interference. This is a dark fringe, because my starting point is my last ending point. Because in here, this is actually where the sum is of these two vectors, starting point to point to point to point to point. So there is still interference in here, but it's not as constructive as in the central fringe. So if I can keep on doing this now, the next one is going to be slightly shifted, and then until I get all of the curve in here, then in this situation, I have my constructive interference. So let's take in here the situation where this is my starting point, and I am at some point in the geometry. Okay, so this is a point P in such a way that they all of them, and there are too many of them that they actually form an arc. Okay, n is going to infinity in here. It's very big. So here is the initial one. The initial one's direction was this way. So this is the initial, this is the top one. This is the very bottom one. The direction for the very bottom one. Obviously, it has to be tangent to this point here. This is the actual shift from the top to bottom. So this is the angle beta. This is the actual shift. So this is the bottom. Shift. Okay. Well, I need to find this angle theta and to find the magnitude in here of this intensity. The arc length does not change. The arc length is always n times how many you have in here. You have a huge number, that's fine. You have a huge number in here. So if I take the tangent in here, which is actually the initial point, and they take the perpendicular in it, I know the center of the curvature of this shape is going to be somehow, it's going to pass by the center of this circle. So the center C is somewhere in here on this axis. If I take the normal to this point in here, which is this vector in here, it's going to also where the center is. So the center must be in here because the center must exist on these two perpendiculars. So this is actually the center of the curvature for a point P on the screen. Having said that, this angle beta, which has this side on it, and this side of this angle are perpendicular because the tangent of a circle is always perpendicular to the radius r. So this is the radius r, this is the radius r of the curvature. The distance must be the same, okay? Now, this tangent here, which is this one, is perpendicular to the other one. Now, look at these angles. I have this side of this angle and this side of the other angle are perpendicular. The other side of the other angle and the side of beta are also mutually perpendicular, so this also must be beta. And the sum of these two vectors is here, actually. So this is the actual intensity that I need to find for the actual wave at point P. If I draw the perpendicular from the center of curvature, this is a right angle. This is in the isosceles because these are the two radii. So this angle in here must be half of beta. So this must be beta over 2. And this, because it's the perpendicular, must divide it into 2. This side and this side are also equal. So this must be E over 2. The actual intensity on point P divided by half. This whole distance. From this geometry, you can clearly see that the tangent, the sine of beta over 2 is E over 2 divided by the radius. The opposite divided by the hypotenuse in this right angle triangle. Sine of theta, sine of beta over 2 is equal to the opposite, which is the intensity of the wave divided by 2 times the radius. I need to find what that radius is. There is another way of finding the radius. Okay. This arc length, which is the intensity in the central point. This is E naught actually, because it's the same E naught that we stretched around. We were in the central point, it's the same intensity, but as we move along to find the point P, the arc just has shifted, that's all. So, the distance has just arced, that's all for us. So in other words, in this case, this is E naught. And from this geometry, it's clearly equal to E naught is equal to R times the angle beta, because this is actually a basic shape in here. So the arc length is always equal to the angular length, which is beta, times the radius. So R beta is equal to E naught. the actual arc distance. By the way, this should be in physics 1, okay? I know that you did that when you did the circular motion, okay? The only thing in here is the symbols are used slightly differently. From here, I'm going to find what R is. R is equal to E naught over beta. And sub into that expression, we're going in R, which is in the denominator. So it's give me sine of beta over 2 is equal to E divided by 2 times R, E divided by the intensity at point P. So I'm going to call it EP because I think it's more convenient to call it EP to distinguish it from the central intensity. So this is actually the intensity at point P because we're referring at some point P on the screen. So EP divided by 2R, and 2R is 2 times E naught times R times divided by beta. So beta is going to be in the denominator in here. Okay. In other words, this equals to EP times beta divided by 2 E naught. So I can solve for EP now, the intensity at point P. So the intensity at point P of this wave is going to be E naught times sine of beta over 2 divided by sine, there is no sine in here, divided by beta over 2. Okay, I'm going to write it as beta over 2 because I have beta over 2 in here. When I divide by it, it's going to be 2 over beta, but I'm going to leave it as beta over 2. So now the only thing in here that we have left to do is find what that beta over 2 is, and we're in business. Okay. Remember my initial argument in here that this is the angle theta. Okay. The angle theta is actually the shift in here between each and every one of those. Okay. And the distance traveled in here is going to be related to A times sine of theta. Okay. So A sine of theta is going to be the actual distance times K. This is the actual shift in angle between the initial and the final point in here. Okay. So this is the actual wavelength, wave number, which is 2 pi over lambda. And this is going to be the actual shift in distance between the initial point and the final point. In other words, this is the distance is A from top to bottom, and the shift between the initial and the final is given by the same argument in here. So this wave traveled this distance, which is A sine theta, more than the top one. If I multiply that by K, remember the actual expression has KR1 minus omega t, and the other one is KR2 minus omega t. So when I do the math in here, I will find that the actual difference between the waves, the omega t and the omega t cancel. So I will be left with R2 minus R1, and R2 minus R1 is what I'm calling delta in this case. And delta from this geometry is clearly equal to A sine theta. So from here, A sine theta is the actual shift from the start to the finish, and that is actually the expression that I'm looking for. So here is the expression that at the end of the day I'm going to get, okay? EP, the intensity at some points in here, P, is equal to the eccentricity of the center point times sine of, open parenthesis, a big parenthesis, of beta over 2. So the 2 from the 2 pi cancel, because when I divide by 2, this divides by 2, and the 2 and the 2 cancel. So I'm going to be left with a pi times A times sine of theta over lambda. This whole thing is part of the argument of the sine function in the numerator, divided by beta over 2. Remember, beta over 2 has 2 and 2 cancel. So it's going to be pi A sine of theta over lambda. This is the actual wave amplitude. I need the intensity. The intensity, I, is proportional to E squared, the amplitude squared. So the amplitude in here is going to look like, at some point, P, so this is the actual intensity of the wave. Because everything else is the same, okay? The mu naught, the epsilon naught, whatever is coming from the properties of the medium, they're there. The only thing that difference is the amplitude of the waves, and it's going to be I naught when you square the E naught squared is going to be proportional to I naught squared. So this is the intensity at the central bright fringe times this whole quantity squared, namely sine of pi a sine of theta over lambda divided by pi a sine of theta over lambda, the whole thing squared. That is the intensity that you could have found also using the trig identity. I mean, using the using complex numbers, okay? So whichever way you do it, this is intensity. Okay, this is, as I promised, this is the last derivation that you're going to see. This is a very important result. The third way of looking at this expression, you just take it for its face value, okay? The intensity at any given point is the intensity at the central point times this complicated function that involves theta in it and a in it and lambda in it and this weird looking function. But that is actually something that looks strange because in the limit when theta goes to 0, that is the central fringe. When theta goes to 0, sine of theta goes to 0. So the denominator blows up. And so is the numerator, by the way, because sine of theta becomes 0, this whole thing becomes 0, and sine of 0 is until 0, so you'll have an indetermination of the form 0 over 0 squared. In order to lift this indetermination, you have to use L'Hopital's rule, if you guys remember from your calculus classes. Yes? We're going to use, is that what you call it, L'Hopital rule, or did I call it differently? Anyway. And that's going to actually give you 1 times I naught. So that's going to give you this value in here. That's why trying to find the actual maxima in order to find the actual bright fringes, you really have to take the derivative of this complicated function and make it equal to 0. And that is in function of theta, okay? And find the condition on theta for which the maxima are. This is not an easy function to take derivatives of and actually find the solution for it for different values of theta. It's going to involve transcendental functions that are not easy to find analytically. You have to use a computer to find their locations or where they are. So that's why the formula for this whole business is to simply go with the dark fringes. Very easy to find them. The dark fringes are A sine theta equals to m lambda, where m is positive or negative 1, positive or negative 2, positive and negative 3, and so on and so forth. Once you find where the dark fringes are, you can find where the bright fringes are. And the bright fringes, you can find them if you choose to by taking the derivative of this complicated function with respect to theta. Not this one. This is just the amplitude. The amplitude is not good enough. You really need to find the intensity, which involves this square stuff in here with respect to theta. Once you find the derivative with respect to theta, equate it to equal to 0. That's where the difficulty is. Actually, doing the derivative is not a problem. You can plug it in a computer and you get the derivative for it. But trying to equate that to 0 is really, you have to do numerical solutions, and it's not an easy task to do. So this is everything that we have. We have some minor things talking about the diffraction grading, like this one in here, and I probably will mention it in the lab later on this afternoon. And we'll probably have to talk also in the lab about the circular, basically apertures, where you have that, and the resolution for them. And that is really all there is to it. So in terms of formulas for this chapter, this is the big one: finding the dark fringes. You need that, and comparing them to the double slit experiment, and also finding the intensities, which is the next formula that I have in here. So both of them are extremely central to this chapter in terms of doing your math problem. I mean, you're doing your homework problems, you're doing your problems for this chapter, and in terms of exams and things like that, those are by far the most important ones. Again, you don't need to memorize how you find this formula in here for the intensity, but it's a good idea to be familiar on how to manipulate both complex numbers and actually also Phasors method, and if need be, also trig functions. Okay, as I promised, this will be the last derivation that you're going to have in this class. Still have some problems to work out on Wednesday, And please see you later on at 2 o'clock for the last lab. And that's it. I think we're running out of time today, at least. So let me stop the recording.